Have you ever wondered how do the Maxwell's laws hold good for the case of electrons? Let me tell you. When an electron is moving about its center, that is the nucleus, there is a kind of a dipole motion that is taking place, with the positive charge being at the center, which is at rest, and the electron moving relative to it. When you have this magnetic dipole, this results into a magnetic field. Let's try to understand more on this in this particular part. So let's now move on to understanding about what exactly is the torque that exists in the case of a circular current loop when it acts as a magnetic dipole. We know that the magnetic dipole, due to any particular loop at any particular point, you can simply point this like this, and you're trying to find out the magnetic field. It's going to be, you will take a current element here. At this point, you will try to find out the net magnetic field directions are going to be this. Then we are going to take the components here and here. That's going to give you the net result. So for x greater than r, you are going to simplify, and this is going to become like this, because for x greater than r, because r is going to be the radius of the loop and x is at a particular distance from it, and therefore this is going to be it. Now moving on, if you want to understand it, so this, what basically does this imply is this. So B is going to be given by mu naught into 2m divided by 4 pi x cube. Means there are two cases that we have. One is the equatorial, other is the axial position. So there is only for one case there is going to be a net value of magnetic field, not for the other two cases. Try to figure out for which case you will get this particular value. So if you try to find it like this, and therefore if you substitute mu equals to 1 by epsilon naught for pole strength, if you substitute for m as P, and for B if you substitute this, so you will get that the net magnetic field and the net electric field is going to be given by this. So as a result, what does this imply? That the dipole moment is going to be given by m, which is equals to I into A. Please do not get confused with the magnetic moment and the dipole moment. Magnetic moment is defined as NIA, and that also depends upon the pole strength, whereas this is the dipole moment, so, or it is also known as the pole strength. So I into A, I is the current that is flowing, A is the area. So this is an analog of the dipole moment in the electric dipole moment. In the case of an electric dipole moment, you had the pole strength and the distance between them. Here it is the amount of current and the area of the loop, not the length, it is the loop that we have here. Now, why is this very important? This is very important for the simple reason that when you have an electron that is moving about the nucleus, what is happening at every instant of time, the electron is going to be behaving as a dipole, because you have a positive charge center at the center and you have the negative charge moving around it. Therefore, at every instant of time there is going to be a changing direction of the electric field. As there is a changing direction of electric field with time, if you look into the Maxwell's laws, that tells us that there should be at least a position varying magnetic field. Since there is a position varying magnetic field, so we will say that the magnetic dipole moment is going to be dependent on the case of an electron as well. So what we have on this case, let's try to understand about this. So an electron is a negatively charged particle, obviously with an angular momentum. We know that from the Bohr's principle. A rotating electrical charge body causes a magnetic dipole moment, creating magnetic poles of equal magnitude. But have you ever thought about something? Try to think about it. Why you do not have magnetic monopoles? You have electric monopoles, that is, you have a single positive charge, you have a single negative charge, but you do not have magnetic monopoles. That means you do not have a standalone negative north pole, you do not have a standalone south pole. You always have them in combination. Why is that not possible? Try to think about it. When we talk about magnetic dipoles, the dipole moment points from the magnetic south to the magnetic north pole, and as a result, if you try to understand further, you will see that the electron exists in a magnetic field which obviously exerts a torque. There is going to be a torque that is going to be exerted because the force on it is changing at every instant of time, and the radius is perpendicular to the direction of force. At every instant of time, this is how it is moving. So there is a torque that exists on it. As a result, if you want to find out what exactly is the current that is produced, so the amount of current that is going to be produced is going to be given by a very simple expression, I equals to E over T. What is E? E is nothing but the charge. If I say R is the radius, so we know that something like mv square by R in the case of a of an electron moving in a magnetic field, this is going to be simply given by QVB, or you can also say this is equals to B into I into L. And as a result, if you want to find out how much is the magnetic moment that is associated, you can simplify this. You can see that it's equals to EV divided by 2 pi R. Just trying to simplify this, you get the expression of V from here. So if you use this, you can find out what is the value of magnetic moment. Magnetic moment is nothing but I into area. Here if you take the area, means the path of the electron to be in the form of a circle, so that gives you pi R square. So this comes out to be equals to EVR divided by 2. Now, what is going to be the direction of the magnetic moment? The direction of the magnetic moment is going to be given by the right hand thumb rule. So you know that the magnetic moment can simplify everything. You can write it like this, but m into v into r, this is nothing but the angular momentum. So if you say that this is nothing but the angular momentum, here E divided by 2m, so E divided by 2m has a special significance. So what we try to say here is this: we have mu L, that's equals to E divided by 2m into the angular momentum, right? Now if we try to find out what is the magnetic moment per angular momentum, so this particular thing is given by, this is known as the gyromagnetic ratio, and according to Bohr, what we have, the angular momentum is nothing but an integral multiple of h over 2 pi. So this is the Bohr quantization. So according to this, electron cannot have continuous values of angular momentum. There are only discrete values which are possible, and as a result, the magnetic moment of a electron is also discrete. There cannot be all possible values that an electron can actually take. Okay, so now moving on, if I say that there is just a single electron, so if I take n equals to 1, that will give us the minimum value of this mu L. So that will come out to be equals to E divided by 4 pi m into h. H we know is equals to 6.67 into 10 to the power minus 34. That gives us the minimum value of the magnetic moment, which is this particular value. The minimum possible value that we have is also known as the value of the Bohr magneton. Let's try to understand further with the help of an example. So what we have, a circular loop of radius r carrying a current I lies in the xy plane with a center at the origin. The total magnetic flux through xy plane is going to be what? Directly proportional to I, directly proportional to r, inversely proportional to r, or 0. Now we know that the number of magnetic field lines which are entering the coil are going to be equal to the number of magnetic field lines that are leaving the coil, and therefore I am talking about in the case when there are no external forces that are acting. I am just saying that there is a current loop that of radius r, and some amount of current is getting, some amount of fields are coming in, and similarly same amount of field should be going out. So the net flux, the net change in the magnetic field lines going in and coming out has to be the same. The net flux through the coil has to be equals to 0. So hope you liked it. As we understood, when the electron moves about the center, there is a magnetic field that is produced. This magnetic field is also time varying. The reason being the direction is changing. If there is a change in direction, then we can apply the Maxwell's laws to define the time varying or the space varying electric field. This is a very, very important concept. This concept that we have also understood also brings to us the concept of the Bohr magneton. Bohr magneton is a very, very important concept in the sense of practicality as we saw it. So hopefully you enjoyed till this point. Stay tuned for more.